Hi, my name is Greg Tracy. Together with Calvin Yu, we'll be going over our final project for spring 2024 titled Outcome Prediction and Consciousness Detection in Patients with Acute Traumatic Brain Injury. Patients with acute traumatic brain injury, or TBI, often remain unconscious, making their long-term outcomes difficult to predict. By improving our prognostication methods, we can significantly enhance the delivery of patient-centered care and the efficient use of medical resources. Historically, our ability to predict outcomes has been limited, but we're aiming for greater accuracy. Our goal is to leverage advanced diagnostic techniques like EEG and fMRI, along with other factors that influence consciousness, to better predict patient outcomes. Referring to the Glasgow Outcome Scale Extended, or GOSE, we'll try to improve our prognostic methods. This task addresses the pressing need for accurate patient prognosis to inform treatment strategies despite the challenges posed by limited data. We build upon prior research such as Clausen et al.'s work on brain activation detection in unresponsive TBI patients using EEG. Their findings highlight the complexity of the brain's response to commands post-injury and the prognostic implications. By tracking patients for up to a year and using the GOSE scale for outcomes, we can further refine detection and prognostication methods. Another cornerstone is the research on predicting functional outcomes in acute ischemic stroke through a deep learning model that fuses imaging and clinical data. By measuring the modified Rankin scale score, this work provides a benchmark for disability assessment in stroke patients, which we can adapt to TBI prognosis, aiming for a high prediction accuracy within a clinical context. Our dataset is generously provided by Professor Lin and his colleagues from Taiwan, consisting of EEG trials and MRI scans of 109 responsive and 17 unresponsive patients. And we have an exciting update. Since last semester, our dataset has expanded with an additional set of data of 28 new patients, allowing for more robust analysis and findings. We propose a comprehensive scope of work that includes system integration of prior research, conversion from binary classification to the nuanced GOSE scale, and a streamlined processing pipeline to enhance efficiency. Improvements to our data preprocessing methods and model upgrades for both MRI and EEG analysis are also planned. Ultimately, our goal is to publish these significant findings. As far as schedule, you can see that we made quite a bit of progress this semester. However, some of the tasks related to model integration have taken longer than we originally thought, and we're still working through some issues, which we can talk about more later. So let me quickly go over our approach again. We're simply taking the combination of the outputs of our image classifier model and our EEG support vector machine to make a determination on consciousness level. The combination is done through ensemble stacking, where you're weighting different models and finding ways to assign appropriate emphasis or normalization to the influence of one model's input over another. Going into the development environment now, this work requires a lot of compute. To support our advanced deep learning models, we've invested in a powerful in-house workstation equipped with NVIDIA Titan RTX GPUs and a AMD Threadripper Pro CPU. This setup has enabled us to centralize development and accelerate iteration, much like having our own local version of Colab, but with the power to parallelize across multiple GPUs. Here are a few images showing some of these hardware improvements. You could see 4 of the GPUs and then cabling that leads to 2 additional GPUs in the shelf below. It takes quite a lot of power to run this, so we had to connect 2 separate power supplies to the system. We have also retooled our MRI training code for simplicity and speed, improving the installation process for necessary dependencies, as well as moving away, or rather, we attempted to move away from slow MATLAB-based MRI image generation, but we decided that even though we'd prefer to use Python to do some of this pre-processing, MATLAB might be slightly faster. So we've decided to leave it as such, but we're open to converting everything to Python torch libraries in the future, or using NumPy. Doing this should really help with our future efforts to have information flow through our setup much faster and much more efficiently.
Here is a recap of our MRI model design. So from our last semester and work from this current semester, we modified a neural network of the ResNet, popular ResNet 50 architecture. We modified it to support 3D input data, as well as to support multiple channels. Channels for MRI data can be represented in the form of different imaging techniques. So here are some types of techniques that are used in clinical practice. This architecture was implemented using Keras and TensorFlow. We trained it using our local setup that we built up using 2 NVIDIA Titan RTX GPUs, each with 24 gigabytes of VRAM. And right now it does binary classification of the patient's outcome, whether they are responsive or unresponsive. Throughout the semester, we made improvements to the 3D ResNet model. First thing we did was to prune the 3D ResNet model by removing an entire layer, hoping to reduce the amount of training time required and the VRAM usage. We reduced the amount of convolutional filters. We also implemented distributed training using Mesh TensorFlow. This meant that we were able to split the model among various GPUs, so that way we can share the VRAM, because this was a VRAM intensive model. And lastly, we want to be able to handle asymmetric data. So in our data processing pipeline, we did something where we centered the MRI slices. So we were looking to accumulate stacks of MRI slices that were closer to the center of the brain. So if you look at if you're facing somebody directly, maybe the brain is going to be the widest portion of somebody's skull. So that's what we meant by centering. As I just mentioned, we refactored the model to implement model parallelism. This means that we can distribute the model among various GPUs. Since we had 6 GPUs, we were able to split the model to the layers in this model to different GPU devices. So this would allow us to take input data that is very large, because one stack of MRI images and the convolutional filters and the processing that does during these layers produce really large arrays, and we need a lot of memory to hold those arrays. So that was one of the main challenges we were trying to overcome. The other challenge was to improve our data preprocessing. So there was a library called Torch.io that was specifically made to handle MRI imaging data and to represent it in data structures that are very friendly to the PyTorch model of implementing different deep learning and AI learning architectures. One of the goals of this semester was to explore the feasibility and the performance of using a vision transformer model on our classification. Transformers have been very prevalent in the previous years, so we wanted to see if the work that has been done on transformers would translate into a robust classification model for our needs. So here's a little recap of what the vision transformer does. So for vision transformers, we take an image, and the image is split into fixed size patches. where each of these patches are linearly embedded via their positions, and a sequence of vectors are fed into a standard transformer encoder. Based on the seminal paper that we read about vision transformers actually attain excellent results compared to the state-of-the-art CNN networks, and consequently, it also requires substantially less computational resources to train. Here are some metrics in comparison to the state-of-the-art models by using the vision transformer model. So as you can see, it performs extremely well on general image classification. So we hope to adapt that model, but now with 3D images. So there are some preliminary works done using something called the 3D transformer model. So like the regular transformer model, instead of single layer, single one-dimensional, two-dimensional images with embeddings and patches, we do three-dimensional patches of an input stack of images. So you can see here, an MRI stack of images is split into fixed blocks, and they are subsequently linearly embedded to position embeddings, and then these vectors are fed into the standard transformer encoder that is the exact same as the encoder used for the vision transformer model. We did this in PyTorch, and we were able to get some results. So we trained this 3D transformer model with the same data set that was provided by Professor Lin. We had 66 patient records. We did a 70-30 train split, training test split. This meant there was 46 training records and 20 testing records. We trained it using 3 input resolutions, similar to the previous experiments done with the 3D ResNet. We have a 128 by 128 by 64 input data resolution, followed by 256 by 256, and lastly 384 by 384 by 64. The first experiment was done on the 128 by 128 by 164, and we centered the MRI stack of images, exactly what we did for training the 3D ResNet. We trained using 50 epochs, and the training accuracy reached 80.43%, and the testing accuracy was 85%. The training loss and testing loss were pretty comparable to what we saw in the 3D ResNet training. We will evaluate the comparison of the results between the two models towards the end of this presentation, but so far these results look really promising. Next, we did a 256 by 256 by 64 input data training, and we trained on 50 epochs again, and then for this configuration, we achieved 91.3% accuracy during training and a testing accuracy of 80%. And the training loss and testing loss, again, were very similar to, if not better than the 3D ResNet counterpart. Lastly, we had an input configuration of 384 by 384 by 64 resolution. We attained 80.43 training accuracy with a 85% testing accuracy, followed by similar training and testing loss values. Here's a comparison of the accuracy and loss between the 3D ResNet and the 3D Vision Transformer. So from a few months ago, when we ran experiments for the 3D ResNet, these were the training accuracies and the testing accuracies that were achieved for the ResNet model, and these are the current results for the Vision Transformer model. As you can see, they're actually very comparable. So This tells us that this is a very much a viable model to use for our classification purposes, and as well as the testing accuracy is very consistent among the different input configurations. Similarly, the training losses are very similar. However, we could say there is a slight advantage with respect to the vision transformer when it comes to the performance on the testing loss, as they're more consistent, and that tells us there is less likely for the model to overfit, even though we only have a limited data set. So what are some of the observations and conclusions from these experiments and the work that we've been doing on the imaging model? We noticed that there are diminishing returns on performance when using higher resolution input images. So when we went from 256 by 256 to 384, the performance didn't really change. In fact, you could argue it actually got worse compared to the 256 by 256. Based on our observations, that seems to be the sweet spot in terms of performance and training time and resource requirements. Again, they show comparable performance. Testing loss on the 3D transformer model is preferred, and based on the outcomes of these two models, it reiterates the importance of how a limited data set can be a constraint for robust models like the ones we've been exploring this semester and previous semesters. So with that being said, here are some of the remaining works that we like to accomplish outside of this course. We still are facing issues with troubleshooting a multi-GPU setup. These issues arise because we're using a pretty unconventional workflow where our input data points are large three-dimensional matrices, and that is not a typical data set or data point for training to train models. Alternatively, instead of splitting the model into multi-GPU distributed training, we could try to look into using one single high-performing GPU with a lot of VRAM. So this would require perhaps maybe a high compute instance on Google Cloud or Amazon Web Services. We'd like to improve the ensemble stacking criteria. Right now, we are still not set on how to integrate the EEG outcome with the imaging model outcomes to have a stacking criteria and a weighting criteria. So that's something we definitely want to continue exploring. Instead of increasing image resolution for our training, we like to increase the channel dimension. Right now, we're only taking a couple of dimensions of the data, so there's still a lot of unused data from our patients that we can leverage, and we could leverage this by reducing the overall resolution of an image, but expanding the types of images that we use. And when we say channel dimension, we're talking about images from different techniques performed on the same patient. Next, we'd like to improve the EEG model by, again, exploring transformer-based models, and hopefully we can see some benefits of using that compared to our more simple SVM support vector machine model. We'd like to inquire with physicians to label patients with a GOSE score. Right now, patients are identified in a binary classification of just simply responsive or unresponsive. However, we want to be able to train a model that is on a more dynamic basis, where we have a score based on a GOSE score where someone is very likely to be responsive, and then different classifications in between that. Next, incorporate new patient data into training and testing results. Because our models are robust and are very similar in performance currently, we like to increase more the data set and use a vision transformer, because as the models scale and changes that happen, it's a more efficient model in terms of resources and computational time. We still need to generate the ROC and AUC curves for our results, and that'll give a better representation of the performance. And lastly, we like to refactor and the submission of our work, and then hopefully we can get that reviewed for a publication. Here are our major references. And if you have any questions, please direct it to us at our Gmails. And thank you so much for listening, and it's been a pleasure.